today we are here with Dr. David E. Nichols. He holds a PhD from the University of Iowa, and he worked for a number of years, most of his career at Purdue University in Indiana as a molecular pharmacologist. And today we will be discussing psychedelic drug research with Dr. Nichols. So the first thing I want to ask you, Dr. Nichols, is you obviously have a very vested interest in the field of psychedelic research. What brought about that? Was it your time in graduate school at the University of Iowa with your PI? How did you come about that interest?
Well, actually, when I wanted to go to graduate school to study psychedelics, I had a number of friends who I graduated from high school with. 1962 is when I graduated from high school. I lived at home, and there was no psychedelic use in the area where I lived. In fact, in Cincinnati, where I commuted to go to school, they had a street named Calhoun Street that had a bunch of little hippie shops with leather sandal makers and paraphernalia and whatever. And the police came in and declared them all fire traps and shut them all down. So there wasn't much going on. But I had friends who went to University of Kentucky, and they were all smoking marijuana, and a lot of people were using LSD, and that had just started down there. So I got very interested in studying that. I wanted to go to graduate school and study it because I'd always been interested in chemistry and science. But I couldn't find anybody who was doing that kind of research in the United States. You go to the director of graduate research and look through all the departments, and nobody was doing it. University of Iowa, the head department there named Joe Cannon had been working with atropine-related compounds that are very potent modifiers of consciousness. In fact, very toxic, produce a real, actually psychotomimetic effect, really more like schizophrenia than anything. So I got accepted there and went to work for him, and we had an interview, and he offered me some projects on some compounds related to apomorphine, which is a drug that makes you vomit. So I said, well, aren't you working on these other compounds anymore? And he said, no, I'm working now on these apomorphine analogs. And so he gave me a spiel about him. Most of the literature was in German. I had to take German for my bachelor's degree, reading German in chemistry. But I was not interested in reading a bunch of literature in German literature on these compounds. They looked fairly uninteresting. And I think he had a Defense Department grant, and the idea was that if you made some really potent drugs that made people vomit, you could fly over enemy troops and spray them with the stuff, and they would all be vomiting. So they couldn't work. So that was really not what I envisioned. And I thought, well, what am I going to do? He had applied to get a fellowship for me. I had what was called a National Defense Education Title IV fellowship. After Sputnik went up, there was a big press in the United States for funding STEM careers. And so in chemistry, that was included. So anyway, he said, but you don't have to work for me, even though you've corresponded with me, you can talk to the other faculty in the department and see what they're doing. And if you want to work for somebody else, that's perfectly fine. So it was a small department. There were only 2 or 3 other faculty. One of them was an analytical chemist who, back in the days before HPLC was a reality, he was analyzing for DDT residues in plants. And the other was a guy named Charlie Barfneck, who had been working on isolating contraceptives from plants and also looking at some anti-inflammatories. So I talked to him, and he said he had a graduate student who was making mescaline metabolites. I said, mescaline metabolites? And what's that chemistry? So he outlined what this fellow was doing. The fellow was totally incompetent as a chemist. And I looked at what he was doing and I said, why is he doing this? This is the wrong kind of chemistry. This is a dangerous reaction. He shouldn't be doing this, et cetera, et cetera. And this is 1969. So Sasha Shulgin had just published a big paper in Nature called Structure-Activity Relationships of, I think, one-ring psychotomimetics. But it was a summary of all the work that he had done to that point for the previous 5 years or so on just derivatives of mescaline, analogs of mescaline. And I knew everything that was in that paper because there just wasn't much literature. So I started a dialogue with Charlie Barfneck, and He actually didn't know that much about the field. I'm not sure why this student was even working on mescaline metabolites, because mescaline is not really metabolized very much.
Mm.
So he started asking questions and I had all the answers, and he got really excited because he realized I knew a lot about the field. And I also had a fellowship that paid my tuition, paid for my laboratory supplies, and also gave him a stipend. So he said, well, yeah, you could work for me if you want to. And so I decided to work for him, even though he had not published anything in the field, but it offered me the opportunity to work in this area. So that's what I did. And he basically turned me loose in the lab and let me do pretty much what I wanted to do. So that was a lot of fun. And also I should point out, I graduated from high school in 1962, and I went to University of Cincinnati and studied chemical engineering for 2 years. But it had nothing to do with chemistry. It was all math. And my father had told me, well, if you like chemistry, you should go into chemical engineering. And there's nothing about chemical engineering that resembles chemistry at all. It's about the size of the heat exchangers and how fast you stir a big, a 10,000 gallon reactor and things like that. So I dropped out after 2 years. I just really hated it. Wasn't very good at math anyway. And I thought, well, I'll go to night school. University of Cincinnati had an extensive evening college division. You could actually get a PhD at night. It would just take you a long time to do it. So I started taking some classes because I didn't have the money to go to school full time. And that's why I lived at home when I went for my bachelor's degree. My parents didn't have much money either. They had the first semester's tuition. And University of Cincinnati allowed you to co-op, so I could work, earn money, and pay my own tuition while living at home. Not a great experience. I wouldn't recommend it to anybody. But anyway, I lived at home, and so I started taking classes at night and working in the daytime. So I worked at local chemical industries around the Cincinnati area for about 6.5 years, working in the daytime. And then after work was over, going to University of Cincinnati and taking classes till about 10:15 every night for 4 nights a week.
Wow.
And I did that for a long time. So Professor Cannon, when he offered this project to me, he kept saying, you can wrap this up. This will be really easy for you. You'll be out of here and you can go get a job and start making money and supporting your family. Well, I had a wife and a little baby. So he thought I was anxious to get back and start working again. But for the previous 6 years, I'd been burning the candle at both ends. So I wasn't really interested in getting out quickly because, imagine you get up in the morning, you go to work and work full time. Then you don't even go home. You go to university and you take classes for 4 hours every night for 5.5 years or whatever. I didn't want to go back to that really. And so in graduate school, I had to take 2 advanced classes in chemistry, which I loved. And the rest of the time, I just basically did research in the lab. So it was almost like a vacation. So I was really in no hurry to finish my degree, even though I finished it pretty quickly. So it was just a lucky coincidence that Charlie Barfnick happened to be at University of Iowa, or I don't know what I would have been doing. So
most of your training is as an organic chemist, from what I can tell. You obviously now seem to know a lot of pharmacology about receptor bias signaling and even things like brain connectivity, the Robin Carhart Harris group stuff they do. How did you develop a bunch of that knowledge from being an organic chemist?
So my PhD is not actually in organic chemistry, it's in medicinal chemistry. So we had to take all the chemistry courses that a PhD for chemistry would take. But in addition, we had to take pharmacology, biochemistry, courses of statistics, things that you wouldn't necessarily take as a chem major. And I did well in all the chemistry classes. In fact, at University of Iowa, at least when I was there, the medicinal chemistry students had a track record of doing much better in the chemistry courses than the chemistry majors did.
Interesting.
So I picked up a lot of pharmacology, and then we were right next to the medical school. So Joe Cannon and Charlie Barfnick both had collaborations with J.P. Long, who was the head of the pharmacology department. So when I would have a reaction running and I had some downtime, instead of sitting and doing puzzles or something, there was no internet then, obviously, I would go over to the medical school and I would watch what was going on in J.P. Long's lab. So I was kind of a pharmacology groupie for those 3 years that I took to do actually my PhD. So when I finished up, I thought, well, I'm right here. I could do a postdoc in pharmacology. And the head of the department had been a collaborator of both of Joe Cannon and Charlie Barfnick. And he had a student who had been trying to get a compound that he wanted. He was in an MS PhD program, MSMD program, and he was looking at the effects of various natural terpenes on mice. And he had one compound that he hadn't been able to get because a student of Barfnick's didn't really appreciate the chemistry and had screwed it up. And so sometimes he would give this compound to this fellow, Jim Engelbrecht, and he would test it, and the mice would get excited, and then he would get another batch, and the mice would be sedated, and he couldn't figure out what's going on. So I talked to him about testing some of the compounds I had made, and he said, I'm really worried about getting my master's thesis done. He said, but I've got this one compound that this other student at Barfnick's can't make. If you could make that for me so I could test it, that's the last piece of data I need for my master's thesis. And then I'd have time to test yours because I'll have time before I start medical school. So I went in the lab a couple of weekends and I made, 10 grams of this stuff and crystallized it, really beautiful stuff. And I put on the label. Back in those days, we didn't have word processors, but they had these things called rub-on letters. They were plastic sheets that had chemical symbols printed on them. And if you'd lay it on a piece of paper and rub on it, and rub on the back of it, it would transfer. They were transfers. So my thesis was all made with these transfer things. So I made a little label that put the name of the compound, and then for the company that made it, I put Sheer Grace of God Chemical Company. So I went over to the pharmacology department, I was walking through the hall, and I ran into J.P. Long, who was the head of the department, who was also Jim Engelbrecht's professor. And I gave him this bottle, and it was I don't know, I had 20 grams, and it was quite a bit. And I gave it to him, and he looked at the label and said, Sheer Grace of God Chemical Company, and just broke out laughing. And I said, I'm going to finish up pretty soon. I just wonder whether I could do a postdoc with you. And he said,
oh, okay.
So I finished actually writing my thesis and defending it. I think it was January of 73, something like that. The official degree was like in June of 73, but I finished the work and wrote my thesis and was out of there, I think in early 73. So then I moved over just to the pharmacology department and started a postdoc there until I was there until November of 74. So not quite 2 years. But I was working in the lab, learning how to do pharmacology, do experimental design, test animals, mice and rats, etc. So that proved really useful because when I moved to Purdue, there was no pharmacology people that were interested in these compounds. They were called psychotomimetics, meaning psychosis mimicking. So nobody was interested, no drug companies were interested. So I had to do my own pharmacology. But having done that postdoc in pharmacology, I knew how to work with rats and mice and even cats. And so I started doing my own pharmacology and started reading more and becoming more involved in pharmacology. And I actually had although I was appointed a professor of medicinal chemistry and pharmacognosy, I was doing work and collaborating with people in the Department of Pharmacology and Toxicology, and eventually was given a joint appointment in pharmacology and toxicology. So when somewhere around 96, I think, they decided to merge the two departments. So I had worked with the people in pharmacology. The pharmacology people all liked me. They were suspicious of some of the medicinal chemistry people because they were all doing cancer research, and they'd been taking more and more space for their cancer research. So they thought I was somebody that was trustworthy. So I became the interim head of medicinal chemistry and pharmacognosy and of pharmacology and toxicology. So for about 2 years, I was the head of both departments. We merged the two departments into the Department of Medicinal Chemistry and Molecular Pharmacology, but I had a joint appointment. And actually, when I retired, I was actually a distinguished professor of medicinal chemistry and also the Robert C. and Charlotte P. Anderson Distinguished Chair in Pharmacology. So I published in both worlds, and I trained pharmacology and neuroscience students as well. So I just developed that, but always had an interest. When my BS degree was chemistry with a minor in biology. So I always had the biology interest. As far as the brain scanning and stuff like that, most of that math is above my pay grade. But regular pharmacology and receptors and so forth, I appreciate that quite a bit.
Yeah, I do as well. One of the most fascinating papers you guys ever put out is we spoke about is the serotonin 2B crystal structure paper, where you guys discovered the diethylamide moiety. It kind of has an interaction with extracellular loop 2.
Right.
And when you mutate that extracellular loop to a different amino acid, the receptor that acts like a lid and it kind of kicks the LSD out of the receptor. Could you briefly discuss I mean, a lot of that paper comes from also the research you had done with the azetidide compounds, the SSAZ and RRAZ. Could you
Yeah.
kind of talk about that a little bit more?
So my last graduate student was a fellow named John McCorvey. And he actually, when he finished his PhD with me, he did a postdoc with Brian Roth, which is with the lab where I work now. And one of the things that John had done, we had started looking at models, receptor models, homology models, and we had developed a homology model of the serotonin 2A receptor. And there was a computational chemist named Marcus Lill who was there. And I also had some students in my lab who learned how to do docking and modeling and so forth. So we had docked LSD in a homology model that we built off of the structure of rhodopsin. The structure of rhodopsin was published, I think, the crystal structure, I think, was published in 2001. And I had a fellow named Jim Chambers, who was a graduate student, who was very computationally friendly. And he did some molecular dynamics to activate that. We had the inactive form of rhodopsin, which is what they published. And so what he did was he, in silico, isomerized the cis-retinal to trans-retinal, so it would have activated, and then used the computer at Purdue to do rigid body dynamics and make that an activated receptor. And we then converted into the 2A receptor by just in silico mutating the residues. So we did some docking studies with LSD, and it was pretty clear that the diethyl groups were projecting out toward the extracellular face of the receptor. And just looking at that, it looked like there was this extracellular loop 2, which is the piece that connects the top of helix 4 to the top of helix 5. And it looked like that was right there and could interact with the diethylamide thing part. So John McCorvey mutated the 3 residues in that loop that were close to where it looked like the diethylamide was, and found that there was this one residue, is a leucine 229, that seemed to be the most important. So when we mutated that, it had the biggest effect. We also had made those azetidides, the 4-membered rigid analogs of LSD, and we had one called the SS and one called the RR, and the SS was the one that was most like LSD. And it also behaved similarly when we were looking at affinity of the receptors when we mutated that leucine 229. So we basically didn't publish much of that. It's in John McCorvey's PhD thesis, but it's in his thesis. And so when he moved to Chapel Hill and Brian Roth got more interested in doing work in this area, Brian had brought a crystallographer named Daniel Wacker from Scripps, and they were working to crystallize the serotonin 2B receptor. I made some LSD so we could do that because LSD was not available. So we made some in-house, put it in there, and lo and behold, when the crystal structure, we looked at the crystal structure, there was that leucine 229 that was poking down in the structure. So John McCorvey, when he was there, did some receptor kinetics and found normally when you do a receptor binding study, you incubate it for say 30 minutes, 15 minutes, 30 minutes, whatever. What he found was in order to get when you put LSD in there using tritium labeled LSD, when you put that in the receptor preparation, it took 3 or 4 hours to actually equilibrate. And then when you wash off all the supernatant and then just put fresh buffer on and look at the efflux of tritiated LSD back out of the receptor, it takes about 6 or 7 hours for it to come back out. So we said, wow, so that residue is affecting the residence time of LSD in the receptor. If you actually look at the crystal structure, what you see is that leucine 229 packs down next to the LSD and wedges it over against the tryptophan that's in there, so it traps it in there. So then we mutated that to an alanine, which we had done already at Purdue, but John mutated that residue to an alanine, and now the receptor connects, LSD got in fast and got out fast. So we clearly proved that residue was really important to locking it in there. It probably also explains the high potency of LSD. You know, LSD, they said years ago, when you look at, if you look at blood levels of LSD, plasma levels of LSD, the effects of LSD come on after the plasma levels drop way down. So there was speculation in the early years that LSD wasn't effective itself, but it was sort of a catalyst that initiated the psychedelic intoxication after the LSD had cleared the body. So, because nobody can understand why it took so long, and then the plasma levels of LSD were so low, and the effects were just starting. So what happens is LSD comes around at those low concentrations, and some of it gets trapped in the receptor. And every time you have fresh blood passing through with some LSD, a little bit more creeps in, gets lodged in the receptor until it builds up to an effective concentration. And then it stays there for hours before it comes back out. So that was really interesting. And the azetidides, what we'd done was realize early on that it was well known that any change of the diethylamide had a major effect on the pharmacology. So if you change the LSD diethyl groups to dimethyl or methyl ethyl or methylpropyl or dipropyl, made any change up there, the activity of the molecule dropped by about tenfold. So we knew that those diethyl groups were critical to the high activity. And we tried to envision a way that we could test the idea that ethyl groups had to be in a specific orientation in order to bind. And so with those 4-membered azetidide rings, we put dimethyl groups on them. And it's a 4-membered ring, so it's like a rigid diethyl amide, or like a rigid diethyl groups. And so those 2 methyl groups, they can either be on the same side, which is a cis molecule, they can be on opposite sides, an RR, or opposite sides, an SS. And so we made all 3 of those, and it was only the one that was SS that had the SS configuration for those 2 methyl groups that was LSD-like in its activity. So then after we got the crystal structure of LSD bound, the real test was we'd written up the paper and published it in 2002 on the azetidide analogs. So when we got the crystal structure, what we did is superimpose the 2 azetidides and showed that in fact the active conformation of LSD when it was bound in the receptor was just like the SS azetidide. We could superimpose the 2. So we had predicted the binding conformation of LSD in 2002. We didn't publish that crystal structure, I think, until 2017, so 15 years earlier. So that was kind of a nice feeling to see that something we predicted that early on had really given us some insight.
And that's really interesting because, that change in substituent at the diethylamide has massive effect on potency and efficacy of the drug. But when you make structures like ALD52 and ethlad, which are, either changing the indole nitrogen or the tertiary nitrogen, the effects actually stay pretty strong as LSD, don't they?
Yeah, well, the ALD compounds, and there's now a 1P LSD and
Yeah.
1P LSD,
And a
1B
1B LSD.
Yeah, those are probably prodrugs.
Right.
With the ALD, it's hydrolyzed off pretty quickly, and there's studies with 1P LSD that it's hydrolyzed off pretty quickly. We made a series of those N-alkyl LSDs, the N6.
Yep.
LSD has a methyl, so we made the ethyl, ethlad, the propyl, prolad, the allyl, allad. We made bulad, and we made a bunch of others. And the propyl and allyl and butyl were actually the most interesting. And at least in animal studies, the ethyl is a little more potent than LSD. And I think we sent some to Sasha Shulgin, and he has it in one of his books. And it actually is a little more potent than LSD.
Wow.
But it has different pharmacology, which we've never published on. And that ethlad is actually a full agonist. If you look at the ability of LSD to stimulate the 2A receptor, it only partially activates it if you're looking at the phosphoinositide signaling pathway. Whereas with the ethyl on there, it's a full agonist. It's actually better than serotonin. Wow. So it has some different pharmacology. It's probably it would be a very interesting molecule to study clinically. That probably won't happen anytime soon. But so that part of the molecule, you can tolerate some larger groups there. And ethyl probably is the best. Although I think allad, these became so-called research chemicals after we published on them, right? So I think allad has been out there, ethlad has been out there, and 1P ethlad I think is also out there.
Cool. One of the more interesting things I'm kind of interested in a similar avenue is you sort of docking and molecular interaction. And one of the things I find really interesting in that paper and a lot of intoxicating drugs in G protein coupled receptors is that when you sort of generally when you bind a drug to a G protein coupled receptor, the top of the receptor where you bind the drug kind of closes a little bit, and the bottom sort of opens because the ionic lock breaks
Right.
that's attached to helix 6. And you have your G protein that couples to it, and a lot of these psychedelic drugs and intoxicating drugs are arrestin biased. They produce arrestin biased signaling. Have you guys ever tried to preferentially prefer another pathway in the serotonin binding? Have you seen like maybe cyclic AMP being inhibited greater than beta arrestin being signaled for?
So the people in Brian Ross' lab have looked at that to a certain extent. Mainly, they're looking at the difference in G protein coupling and arrestin recruitment. LSD recruits arrestin in a time-dependent manner. So if you look at that paper we published on the crystal structure of LSD and the 2B receptor, there's a graph in there that shows you the effect of, and it's actually from the 2A receptor. We have data in there for the 2A receptor as well. And the 2A receptor, the longer LSD stays in the receptor, the more potent it becomes and the higher efficacy it has in recruiting arrestin. So it's highly arrestin biased. But other psychedelics, I don't think have been looked at to see the relative bias for arrestin versus G proteins. And no one, as far as I know, has really looked at differential effects of the different G proteins. There are 15 or 16 different ones: G alpha I, and G alpha O, and G alpha S, G alpha Q, etc. There was a postdoc in his lab years ago named Niels Jensen, who actually looked at a whole bunch of serotonin 2A agonists, phenethylamines, bromofly, and DOI, and some tryptamines, etc., and looked at their effect in 7 different signaling pathways and created a heat map showing the relative strength of efficacy in each of these pathways. And every one of these molecules, although they're all considered psychedelics and they're very similar in structure, they all have different fingerprints, signaling fingerprints. Unfortunately, he left and never finished writing up all the methods, so that never got published. But the qualitative differences between these are probably related to the signaling differences in this receptor. And there may be some other receptors that are tangentially involved. They do have affinity at the 2C receptor, some of them at some other receptors, much lower. So the 2A may be like the switch that turns everything on, but there are other ways that, other signaling pathways that modulate what the actual outcome is. So that's a fertile field for someone to really look at, a library of these compounds and really look at all the different effects they have on arrestin recruitment and different G protein structures. There's a lot of work related to that that's going on in Brian Roth's lab now, which will be published over the next couple of years, looking at, the coupling of a receptor to all these different signaling pathways. So that'll come. It just takes a long time. These are pretty complicated and detailed and lengthy experiments.
Right. I do want to get a little bit onto the Robin Carhart Harris group, which you probably know more about than me, but in a few of his publications, he coined the default mode network. So could you talk about, what the default mode network is and how that relates to the psychedelic experience?
Yeah, so he didn't coin that term.
Oh, he didn't, okay.
But, he's used it quite a bit. So the default mode network was really identified, I think, in the late 1990s or maybe early 2000. I'm not really sure. I forget who did it, so I'm not really up on all that. But when they looked at the resting brain, when people were not doing any kind of mental task, they were just laying there in an imaging machine, just kind of daydreaming, if you will. They found that the brain was using a surprising amount of energy in this one group of structures. And they said, well, and when you do a mental task or something, it shifts there's task-oriented things that happen. But when you're not doing anything and just laying there kind of daydreaming, this area uses a lot of energy. So they said, well, this is a default mode network. It involves, the posterior cingulate cortex, the anterior cingulate cortex, a lot of areas kind of in the center of the brain. So they think that it's sort of as a conductor for everything that's happening in the brain, if you will. and it sits in the middle of the brain, and so it sends a lot of directions out in terms of instructions to other parts of the brain. So if you and so in people that are depressed, they seem to have a lot of brain energy directed in this default mode network to keep they keep the obsessing and rumination, etc. That seems to be directed out of the default mode network. So there are many networks in the brain. If you look at resting state networks, there are anatomically defined areas in the brain where you have always got activity going on. The default mode network is just like one area. And so when you take a psychedelic, what happens is all the intra-nodal or intra-network connections are broken down, including the default mode network. It loses its integrity. So all the structure that's within that default mode network, the structure is basically, it disintegrates. And in all the other areas in the brain where you have anatomically defined areas where you have network activity going on, their structure within those nodes all breaks down. And instead what they do is they start reaching out across and communicating with other parts of the brain that they normally wouldn't talk to. And so he's referred to that as the entropic brain. You have a global increase in communication. So if you look at entropy, it would go way up. So everything's kind of chaotic. So you lose the structure in things like the default mode network, and then everything starts talking to each other. And that somehow that mechanism is related to the therapeutic effects of these compounds. So there's some kind of a reset that goes on that nobody understands at the present time. So when you break down all the network structures and you have this global increasing connectivity, then the drug is gone and everything kind of collapses back, and apparently it collapses into a more healthy pattern if it was dysfunctional to begin with. They know that in most psychiatric disorders, if you look at the resting state networks, they have a dysfunctional organization for OC, obsessive compulsive disorder, depression, all kinds of things. And in at least one study where they've looked at resting state networks of depressed persons and then given them an SSRI, a standard drug for treating depression, in the patients who recovered and the symptoms of depression went away, they've done scanning then to show that the network connectivity falls back into a more healthy pattern. So somehow when you take one of these drugs, it sort of disrupts these dysfunctional, they're called hub failures in the terminology of this network imaging. These hub failures get destroyed, and then things collapse, and if you're lucky, they fall back into a healthy network connection pattern. So that's really interesting work. And of course, the big task for psychiatry is going to be to understand what actually happens. How does that reset occur? And I know I saw a seminar that Robin gave in Copenhagen some years ago, and he finished his talk and people said, well, so how does this happen? So he brought up another slide. It had a big red button with the white letters that said reset on it. And he said, somehow it's like a Control-Delete, it's a big reset. That's the big question. That's what psychiatry is going to have to figure out, I think, and will really give some insight into actually the basis for a lot of these psychiatric disorders. If you find out what that reset is, then you start looking for things that aren't reset and say, well, where are they and how can we fix that? So I think it's going to change the whole idea of using psychedelics to understand how the brain works. I think is changing psychiatry. It's going to change the whole emphasis on how psychiatrists have approached brain in the past. Instead of being pharmacotherapy, like an SSRI blocking the reuptake of serotonin, or a benzodiazepine binding to GABA chloride channels, it's going to really start people thinking about what happened to the networks. What are the networks that are dysfunctional? They're starting to do a lot of that, and a lot of it's been related to the availability of really high-end software and really large supercomputers. And those have just really become available in the last, 10 years. And then the magnetic resonance imaging, the power of those magnets, as well as magnetoencephalography, all these high-end brain imaging tools have really just been developed and come into their own in the last decade, say. And then coupled with the software, and a lot of people writing software to do more and more detailed analyses. So the psychedelics, I think, are going to be proved to be really important tools in just understanding normal brain function, and not just, what's wrong with people that have psychiatric disorders.
So with that, do you envision a world in psychedelic therapy where it's not necessarily legal for anybody to do, but people have access to it if you have like a psychiatrist recommends a psychedelic session with maybe a clinical physician or somebody that's somewhat shaman-like? Do you envision it in that method, or just kind of a free-for-all where psychedelics are completely legal, like, what we're seeing with marijuana where it's completely legal?
Yeah, people have drawn the analogy with medical marijuana and psychedelics. Psychedelics are really not as benign as marijuana. You really can get into psychological trouble in an
Agreed.
unsupervised situation. People have done dangerous things and have precipitated, and people who have a pre-existing liability to, say, schizophrenia, they can really catalyze the onset of severe illness. So I don't think it'll be like that. Somebody asked me years ago what I thought the future would be, and I said, well, someday in the future, probably long after I'm dead, you'll be having a midlife crisis, and your primary care physician will send you down the corner to a psychiatrist slash shaman, and he'll recommend that you do a psychedelic session, and you'll do a session with this person who's trained, and then you'll get a perspective on what's going on in your life and what do you need to rebalance things and so forth, and those things I think will be available, and there'll be trained specialists that know how to use these. Um, she said, "You think that you'll be dead by then?" And I said, probably, but if the vector's moving in the right direction, that'll be okay. Well,
Right.
it's moving a lot faster in the right direction than I ever imagined. But I don't think it'll ever be a free for all. I think what you may see is decriminalization, because to this point, psychedelics have always been touted by the press and the police, etc., as being dangerous drugs of abuse. They can destroy you, yada, 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 yada. And I think once they're seen that they can be therapeutic drugs when used correctly, I think there'll be less of a pressure. And so that, like in Colorado and places where they're decriminalizing psychedelic mushrooms, trafficking in them will probably still be restricted. But if the police break into your house and you're eating mushrooms or something, I don't think they'll prosecute you. I think there won't be juries that'll convict you for that kind of behavior. So I think that'll come. But as far as being everybody able to get these, I think they'll always be kind of restricted. And even in other societies where they used them, the shaman was the one who really was the one who used them. Just everybody in the Aztecs didn't all just run and eat a bunch of mushrooms. The ceremonies were led by the shaman or the witch doctor, whatever, so far as we know. And even in the, like the Greek Eleusinian mysteries, which went on in Eleusis in ancient Greece for 2,000 years, where they drank kykeon. You didn't just drink kykeon in your house on the weekend. It was once a year ceremony. It was held in a building called the Telestrion in a village 15 miles outside Athens. And there were attendants, people that chanted and sang, and there were people there that watched over you. So they've always been used in a ritual kind of context. Now, whether a physician will be, whether you have to have a medical degree to become someone who directs these or not, I don't know. But I think you're going to have some kind of specialized training in order to use them properly, because people will get in trouble with them. They will have difficult experiences. So I think you need people there that understand what's going on. And with all the studies that the Hefter Institute has funded, they've always had a crash cart right there outside the door in case somebody, goes south. They have somebody that can do medical care right away, resuscitate them. You can imagine that somebody who wasn't properly screened, that might have some pre-existing cardiac condition, has a terrifying experience where they're highly anxious and panicking, and so then they have cardiac arrest. Those will probably happen, but if you've got somebody there who knows how to deal with that, you can prevent that. Right now we're screening people. Anybody that's in a Hefter-sponsored study is carefully screened for pre-existing conditions and first-degree relatives with mental illness, etc. But at some point, there's not going to be that much screening, and so you're going to have to depend on people being healthy. I mean, they might always check their blood pressure and have a questionnaire that you fill out, but I think it's never going to be like medical marijuana, which should never have been made illegal to begin with. That's my opinion.
Interesting. You bring up medical marijuana, and the one thing that I do have a little bit of reading into is synthetic cannabinoids. I don't know how much you're probably have read about synthetic cannabinoids like JWH018 and the AME compounds, and those are, unfortunately, if you read a lot of the literature, they're incredibly potent, and they cause pretty bad effects in people. Do you have any information in terms of like how the synthetic cannabinoids, they were originally used as research compounds, and then unfortunately, a lot of people, they read these publications and the chemists can
Right.
redo the syntheses. Do you feel any sort of like, uh, do you feel like there should be restricted access towards some of these publications that people can't replicate the syntheses, or maybe you just leave them out?
Well, the whole basis of science is reproducibility. And so if you publish something, Huffman made those compounds in a program to try to find things that activated the cannabinoid receptor. They're not actually cannabinoids. They're cannabimimetics. They mimic
Mm-hmm.
cannabinoids, but cannabinoid is a specific kind of a tricyclic structure. Um, and of course, if marijuana had been legal, there would have been no market for these synthetic
Mm-hmm.
cannabimimetics. And that's a big problem. I testified in front of a House subcommittee on drugs when they were rewriting the laws and they were trying to make them much more restrictive. And I testified in behalf of scientists who said, you have to allow scientists to be able to work with these to find out how they work. And the Congress didn't understand that when you make something Schedule 1, you restrict it. People, scientists just don't want to mess with it unless they're devoted to drug abuse studies. And a lot of pharmacologists, if you can buy something from a chemical catalog, and there are places like Tokris and some places that sell these specifically as tools for medical research, you say, hey, let's do this experiment. Does anybody sell a compound like that? And you see it in Tokris catalog, you buy it. They're pretty expensive, $100 for 5 milligrams or whatever, but you can do the experiment. You can't do that with a Schedule 1 substance. So if you wanted to study psychedelics, you have to apply to get a license. You have to have a justification for it. You have to have a secure place where you can store it and keep it locked up. It's kind of a hassle to work with Schedule 1 unless that's really what you want to do. It's not something somebody could just say, what if we did this? What if this experiment? And then you just call up somebody and say, I need 10 milligrams of mescaline to do this experiment. It doesn't happen. It'll take you 6 months to a year to get the approvals if you're lucky. And you may have to buy a big safe that nobody can break into it, even for small amounts of these things. So I testified and was saying, you need to write a law so that researchers can still get these, because they don't seem to understand that getting a Schedule 1 license is kind of a real hassle. And then the fellow that testified right after me, was a father whose son had died.
Mm-hmm.
And he said, well, his son had been dependent on marijuana, which is a rare thing to begin with, and they put him into a rehab clinic and got him, cleaned out of marijuana. It was like he was some hardcore addict or something. I'm kind of listening to this. And he went to a party, supposedly. And he said he went to a party and then he just got careless and they offered him the stuff and they said it was legal. It was a legal marijuana substitute. What was it? One of the spice compounds. He said he took one toke and went into a coma and died a week later.
Oh my
Well, that
God.
story doesn't exactly make sense.
Mm-hmm.
But I'm sitting there thinking, if marijuana was legal, he could have just smoked some marijuana and you'd still have your son. So I think the fact that these laws exist have really created more havoc. Marijuana in the old days, when it was grown in Mexico and South America, was maybe 1 to 2% THC, the active ingredient. So people would roll these giant joints and smoke them, and you never got that high. I mean, hashish was a little different matter. But when it became really illegal and they decided to go after the hippies in the 60s, Nixon's war on drugs, it's difficult to smuggle big bales of low potency marijuana. But if you grow it in the United States, you don't have to bring it in from Mexico or South America. And you don't want to have a big, huge growing field of low potency stuff. So you get these high potency strains that have been developed in the Netherlands that produce 18, 19, 20% THC or even more, and you grow them. And so having it illegal really fostered the production of a high potency marijuana that really is more dangerous. It can produce transient psychosis in people who smoke this. I talked to a woman in California years ago who was a fairly habitual smoker of cannabis. And she says, I can't even smoke the stuff they have now. I just take one token, I feel catatonic. It's like 20% THC. So the laws against it have made it, I think, much more dangerous than it ever was before. When I was a graduate student, we never heard about people having cannabis dependence. And now it's a recognized category for people that smoke it every day on a regular basis and smoke, really potent stuff. So the laws, I think, have not helped. I mean, MDMA, which is a reasonably non-toxic compound, people use it at raves or whatever that does 100, 150 milligrams. Sure, people will abuse it, but when they make it illegal, then you get all these synthetic mixtures that people come up with, new compounds, research chemicals that they put together in mixtures, add mixtures. And so people go and somebody says, oh, here's some ecstasy. And they're like most teenagers, they're not really, they're immortal. And so,
Right.
oh, okay, take this. And so then all of a sudden you have a problem. So I think the laws, the way they're structured, have really caused more damage than the drugs potentially would have. Certainly that's the case with cannabis.
Mm-hmm. And it's for sure, it's really hard to structure a drug law around like this drug structure should have this mechanism of action, because when you yourself create a new drug, just because it has a similar structure doesn't mean it'll have a similar mechanism of action. So it's like, how do you rationally say like this subclass of drugs should be illegal when you don't even know what the mechanism of action is? When you could change a methyl on some molecule and it could completely change the mechanism of action. So it's complicated.
Well, the other situation is, when we made analogs in my lab, analogs of mescaline and tryptamines, et cetera, really the only assay we used was for activation of the serotonin 2A receptor. And we used rats which had been trained to recognize things like LSD or MDMA or amphetamine. And we were only looking at a single thing that they did. So like these synthetic cannabimimetics, these spice mixture things, they're really potent in activating cannabinoid receptors, but we don't know what else they do. They haven't been screened to see, well, do they activate this other receptor, this other receptor? Do they activate receptors that control blood pressure, heart rate, or all kinds of other things? So the fact that it activates the cannabinoid CB1 receptor, that doesn't tell you anything about what else it might do, which might be really toxic.
Right. And it's interesting because I feel like we're not at an area in pharmacology yet where we can say this drug activates, 25 different receptors. There's not really an assay that can screen for all of that all at once. You have to run separate assays to measure those things.
Yeah, well, there are places that will assay, like Brian Ross' lab. He has the National Institute of Mental Health funds his psychoactive drug screening program. So if you're a legitimate researcher, you can send a compound to him and say, could you do a complete screen? So he has a robot and technicians that run it that will screen for 70 or 80 different receptors.
Jeez.
It'll take you a while to get all the results, but that's just for affinity. And then if you want function, that's, you find out it hits one other receptor, then you have to do functional assays. You can do it, but it requires a lot of effort, and it's not something that's just routinely done with every new drug that shows up. Basically, you screen it if you think you have got something interesting, and you say, okay, is there anything else that I should be looking at? And so, but not many people use it in that way.
Mm-hmm. One thing I do want to ask you about, because I know you're kind of the pioneer in this drug, is the NBOMe compounds. So the NBOMe compounds are a class of compounds, I believe, from the 2CI family. Where did you get the idea for the NBOMe compounds in the synthesis?
There was actually a fellow in Germany that was dissecting blockers for the serotonin 2A receptor. He had ketanserin. He was taking it apart piece by piece and somehow came to the conclusion that if you had a phenethylamine with an N-benzyl of some kind, that it was active. And he published that, and he had a poster at a meeting. It was in German, and his technician had contacted me, sent me copies of the poster, and said, "These look interesting. Could we collaborate?" And I looked at the structures, and they were so simple. And we were doing all the pharmacology, so I thought, what would the collaboration be for? And so we just made a whole bunch of them, and they turned out to be really potent. Rolf Heim was the scientist who had first reported these in his PhD thesis some years before we found out about him. but he had been testing him, I think, in a rabbit ear artery assay, and we had drug discrimination set up for rats to discriminate LSD. So we thought, well, let's put them in our model and see what they do. And they were indeed quite potent. My research associate, Danuta, who ran the rat colonies, we made one of the first compounds. It was 25I NBOMe, and she started dosing rats. And based on other phenethylamines, she started at a dose we thought would be reasonable. And it turned out all the rats got severe diarrhea when she used it.
Wow.
So then she lowered the dose down, gave that to them, and all the rats got severe diarrhea. So then she lowered the dose even further, and then we found a dose where they didn't get diarrhea, but then they responded to as if they'd been given LSD. So that's when we found it was really potent. And so then we said, well, why is it so potent? What's the benzyl doing? So then another graduate student of mine, Mike Braden, we mutated the receptor and looked at a bunch of different structural modifications of the NBOMe compounds and identified at least one residue. It was a phenylalanine that was in that receptor that was interacting with the N-benzyl. But yeah, those were, I've been sad to see that they've been fairly toxic and killed some people. And I don't know whether it's an idiosyncratic reaction, because everybody that's taken them hasn't died, but only a few have. And it turns out that work in Denmark has shown that those NBOMe compounds there's a methoxy group in the 5 position that's very readily cleaved. And they give it to pigs in their studies. That methoxy comes off almost immediately as conjugated with glucuronic acid. And so it's possible that the demethylation reaction that occurs in the liver that takes that methoxy off, it's possible that there are people that are missing that enzyme or they don't have that particular enzyme. And so the unmetabolized compound stays in the system, and those may be the people that suffer the lethal effects of these. So I think there's some genetic basis to the metabolism. Nobody's really looked at that. There's a lot of interest in these compounds. They are extremely potent in activating the receptor, but why they kill people is not really known.
Mm-hmm.
Yeah, I was disappointed anytime a compound that came out of my lab that killed somebody. If I had anything to do with it, every time I'd see that, it just really would make me sad.
Yeah, that's super tough as a researcher, because you're developing these compounds to try and study the receptor and study a structure-activity relationship. You're not trying to induce those sort of effects. That's hard.
No, I mean, I have no desire to create new research chemicals that people then go and take. It's just not my goal at all.
Something I do want to get into that's obviously popular in this sort of psychonaut community is the pineal glands, and you're probably well versed in N,N-dimethyltryptamine, DMT. Do you believe that our body makes enough endogenous DMT to produce a sort of like DMT release when people die? Do you believe that or no?
No. In fact, I wrote a whole paper on that. In Breaking Convention a couple years ago, I was invited to participate in a panel on DMT, and the person who invited me, the title of the panel was DMT as a neurotransmitter, something like that. And I said, well, I don't believe it is. So you asked the wrong guy. He said, no, that's exactly why we want you to come, because we want you to present the other side. So there were like 3 people there that were arguing that DMT activated a sigma-1 receptor, was produced in the pineal gland, it did this other thing. And I got up and basically said, there's no evidence for that. Strassman has shown that in order to get that kind of effect, you'd have to inject like 25 milligrams of DMT intravenously. And I said, the pineal gland is not capable of producing 25 milligrams of anything quickly. Pineal gland weighs like 180 milligrams. For it to produce 25 milligrams of DMT, which melatonin is its principal product, not DMT. For it to produce that, it's not physically possible. So then there have been all these more papers coming out attacking me, saying, yeah, but it could be produced in the lungs, and the enzymes to make it are all over the place, and you can detect it in the brain, and it's there at the level of other transmitters, and da-da-da-da-da-da-da. Well, I'm just not convinced. It's not there to do that. You may be able to detect trace amounts of DMT in the brain, but it's such a nice theory. DMT is such a potent psychedelic. oh, and the brain produces it. Maybe
Mhm.
something important is going on there. So it's a powerful public meme, but I don't personally subscribe to it.
Yeah, I mean, it certainly is. DMT, you of course made the DMT for Rick Strassman,
Yeah.
in DMT, the spirit molecule, and all his studies. And DMT seems to be unique in terms of psychedelic in that it really just shoots you out of your body. You are no longer attached to your body. You are sort of traveling through the universe as like a beam of energy.
That's probably more true with 5-methoxy DMT.
Is it? Okay.
Yeah, but yeah, DMT, unless you really go to high doses, the observer I think is still in there. But with 5-methoxy DMT, the internal observer is gone. You're just like along for the ride. But it is different in terms of how fast it works, and and some controversy about whether the 2A receptor is the only target. There are some people. Thomas Ray published something saying, "Oh, it activates the 5-HT7 receptor," but it's really that's not a good study.
You almost wonder what's happening at the 2A receptor if DMT is producing such more powerful effects than drugs like LSD. Like, why is it, shooting you out of your body as opposed to LSD, where you're still very much attached to your body, but you are just experiencing reality in a much different way.
Yeah, part of it is probably the pharmacokinetics. If you take a dose of an oral dose of morphine, or even an injection of morphine, it has a certain effect, an analgesic effect. But if you give a large dose of morphine or heroin, which gets into the brain very quickly, there's this immediate, intense euphoric effect. And so when you take anything, when you smoke it, inhale it, or if it was given by injection, it goes into the brain really rapidly. And I think part of it is the fact that the brain has no chance to accommodate. There are all
Hmm.
kinds of feedback circuits in the brain that if you overactivate that receptor, and the 2A receptor is a really critically important receptor. I mean, it's involved in our sort of the foundations of our consensus reality. All the lower cortical structures send input up to the cortex, and that's where all the executive decisions are made and where we form this sort of consensus reality. So if you do anything to muck with that receptor, there are inbred mechanisms that will try to attenuate that. And of course, LSD accumulates in the receptor fairly slowly. If you give it intravenously, it doesn't really come on any faster than if you take it orally, because
Hmm.
it still has to equilibrate in that receptor. But DMT gets in, gets back out really fast. It doesn't sit in it for a
Interesting.
long time. So smoking it or injecting it, you have this rapid increase. So I think it's probably more related to the pharmacokinetics of DMT as opposed to something like LSD, which is much slower, or even psilocybin. Um, and of course, injected psilocybin has a very powerful effect too, like 2 milligrams versus what you would take orally. So Carhart Harris started his studies with injected psilocybin.
Did you have any experience with like the psychedelics like DOI in terms of synthesis, those types of class? I mean, and if you did, could you talk about that sort of research on DOI and DOB?
Yeah, I made DOB actually for my PhD thesis. That was a compound that I proposed to make. And it was supposed to be my master's thesis, but I bypassed the master's and I did all those compounds in like one semester. And DOB was made, I made it about the same time that Sasha Shulgin did. Um, he published human studies, and we just published on some fluorescence studies and things like that. DOI, we developed, when I was a graduate student, we developed the synthesis for making the enantiomers of all these DOI, DOM, etc. Published a paper in 1973 on the asymmetric synthesis of all these. And so we made the enantiomers of DOI, enantiomers of almost all the compounds, and then actually worked with Chet Mathis to develop a synthesis for I-125 labeled DOI, which we used in some studies. And that was available for a long time as a radioligand for doing studies like labeling brain slices, labeling receptors. So we did a lot of work with phenethylamines, looking at stereochemistry and substitution.
Hmm. Something I was reading about that I never had a clear answer to is so LSD has two stereo centers just on its own. I
Right.
believe the 5 position and the 8 position.
Right.
3 out of the 4 diastereomers are inactive. Do
Right.
you know why? Is it like if I injected somebody with the inactive enantiomer, would your body bioconvert it into the active one?
No.
It wouldn't.
No.
Interesting.
So the 5 position is pretty hard to racemize. It's the natural organoids have the R configuration at the 5 position, and the natural organoids at the 8 position also have the R configuration. So that 8 position can go back and forth from the normal to the iso under the conditions of pH. So if you put LSD, which is the normal diethylamide, the 8R, if you put that in an acidic solution, it will convert over to the iso LSD. And if you take iso LSD and treat it with strong base, it'll convert it back to the normal. So in the stomach, if anything, the acid in the stomach would convert normal LSD into iso LSD, which is not active. And LSD is a relatively flat molecule. The diethylamide also lies in the plane of the molecule, but in the iso compound, the diethylamide is almost at right angles to the plane of the LSD molecule. So the stereochemistry at the 5 position, which is more critical, all the amino acids, your body is made out of chiral amino acids. They're all D amino acids. So everything in your body is chiral. And so for things that have isomers, and natural products typically have one enantiomer that's made by an enzyme. The active enantiomers will act at receptors in your body that are made of natural amino acids. So if you switch that 5 position to a 5S instead of 5R, it just doesn't fit. It's a mirror image of the LSD molecule, and mirror image of LSD doesn't fit into receptors made of D amino acids.
The Amanita Muscaria mushroom, and you spoke about the Eleusinian mysteries. And I was reading in one place that some of the compounds used in the Eleusinian mysteries was the Amanita Muscaria mushroom. Do you know, like, is that compound fairly toxic?
The psychoactivity of Amanita Muscaria is kind of controversial. Some people have eaten those mushrooms and had no effect at all. So the active component in there is ibotenic acid, which I think is a GABA agonist. But there are also some cholinergic compounds in there. They're completely different from psilocybe species. I don't know that Amanita Muscaria, they're pictured, they say as Santa Claus with this red shirt, white. It's all reflecting Amanita Muscaria. There's a lot of romance and legends about Amanita Muscaria, but I've talked to people. I talked to a couple who found a whole bunch of Amanita Muscarias and ate them. And I said, what happened? She said, well, my husband and I were both unconscious for like 24 hours, and we woke up.
Geez.
And we're laying on this bed, and we're totally covered with perspiration. We must have been sweating like crazy. It's like just dripping with perspiration. But she said, I wouldn't say it was anything. There was nothing that happened that was really outstanding. We just both we were kind of in a coma, it sounded like. So I don't know. And then other people say, oh yeah, well, it has to be dried, or it has to be cooked, or well, they only produce active compounds when they're grown in certain environments. So it depends on where they come from. So that's still kind of a mystery to me. But the psychoactivity is quite a bit different if it's active than on things like psilocybe mushrooms.
Mm-hmm. Do you at all subscribe to the idea that, I don't know, you read a lot of like psychonaut people talking about psychedelic drugs. So would you at all subscribe to the idea that part of the evolution of human beings could be attributed to psychedelic drug use, many centuries ago? Because as you're aware, old civilizations had it riteralized using psychedelic drugs.
Shades of Terence McKenna.
Yeah, exactly. And you knew Terence, obviously, but yeah.
Terence and I were at a party. We were there early, and he had this theory that mushrooms were aliens. And I looked at him and I said, Terence, the thing that puzzles me is why aliens would make their home in shit. Because they're coprophilic mushrooms, growing cow pies. He just broke out laughing. I don't think an exogenous agent can influence genetics.
Interesting. Okay.
Talk about epigenetics and all, but I don't think that can happen. What I do think is that they may have been responsible for beginnings of religious and philosophical thought.
Mm.
So you can imagine if you assume that the brains, not going back too far, but our brains, say 50,000 years ago, maybe not millions of years ago, but 50,000 years ago, our brains were probably pretty much like they are now, although there has been evolution over 50,000 years. But that hunter-gatherers would go out and find these mushrooms growing in the fields, where cows had been or sheep had been, and they would, eat them, thinking they were, edible, and they would have this experience, this incredible psychedelic experience. So they'd collect a bunch and take them back and say, you guys got to try these. These are really fantastic. And they take them and go, my God, where was that place? I was transported, like the land of the gods and all the things I saw, like who can imagine, we have a lot of education now. So anything that we would have visions of would be colored by our cultural influence. But back then, what was the culture? They lived out, there was the tree gods and the rain gods and the sun gods and the gods of plenty and the gods of poor and whatever. You don't know, but I think they would have the same kinds of experiences in general and say, like, what was that? Where was that? So I think they would start rituals. The shaman would take these things and use them in particular ways. So I think in terms of religious thought and philosophical thought, I think they were very important, but I don't think they influenced the evolution of our brains.
Mm-hmm. Interesting. Yeah, you bring that up.
Stoned ape hypothesis, right?
Yeah, exactly. I started reading about this stuff at a young age before I kind of got more involved in the chemistry. But things that I also read about, of course, is ayahuasca used in the Amazon rainforest. And a lot of shamans, I suppose, will say that the vomiting part of the ayahuasca use is would support purging. It's part of the experience, but as a pharmacologist, you would probably say they're having a toxic effect to the drug.
Yeah, I think it's poorly made ayahuasca that has too much tannin, too many tannins in it.
Mm.
There's ayahuasca that doesn't really produce that. But there's this whole shtick about, oh, you have to purge as part of getting the bad spirits out and everything. I personally don't like to vomit. Almost
Yeah.
never, I don't. So, and there's ayahuasca that doesn't produce vomiting. But I think it's poorly made. They don't really care. And of course, that makes you vomit. They think that's great. You have to vomit. You have to purge.
Mm.
And so all the ayahuasca ceremonies, they give you a little bucket to throw up in, and so I think that's just badly made ayahuasca.
And in terms of like drug delivery, it's really interesting because ayahuasca contains DMT, but in order to make it bioactive, you need a monoamine oxidase inhibitor. But the effects of injecting DMT versus drinking ayahuasca are vastly different. So could you speak a little bit about the pharmacology of that in terms of why that
So
is?
again, that's pharmacokinetics.
Right.
You can inject psilocybin, and you have this within seconds. You have this massive peak experience. But if you take it orally, it's 20 to 40 minutes before it kicks in, and so then you get a couple of hours of effect, and then it tapers back off. So a lot of that is just pharmacokinetics. So the DMT, and I've had known people that have taken both ayahuasca and psilocybin, and they say, under the right conditions, they're very similar. It's just that oral DMT is a lot like psilocybin.
Mm-hmm. Interesting. Would you ever support the idea of people going to the Amazon rainforest to take ayahuasca? Is there anything you think special about that place and taking it with those shamans, or not really?
No, I think it's all this mythology and legends.
Mm-hmm.
They go to Peru, for example. Ayahuasca tourism is because it's legal there. It's not legal here, and they think they're going to find a shaman who's going to work miracles. But I
Mm.
don't know. I don't know how many of those shamans you could trust. It's been so commercialized.
Yeah.
A lot of the shamans are mixing things with their ayahuasca. You hear about somebody dying from a shaman that mixed some tobacco, raw tobacco in or something, and they died of nicotine poisoning. And I know people that went to the Amazon. One fellow picked up a really nasty infection. Some got a
Mm.
parasite in his body and got really sick and came back and nearly died. So I don't know. The idea of sitting out in it may be romantic to sit out under some kind of a hut in the jungle and listen to the birds and all. And that might appeal to somebody, but I'm not sure it would appeal to everybody.
For
But
sure.
it's mainly, I think, just the legal aspect. They've heard all these wonderful things about ayahuasca, and so they buy a plane ticket, and they find somebody down there who does ceremonies, and so they fly to Peru.
Hmm. I also kind of think what's super interesting is you were probably decent friends with, not decent friends with people like Timothy Leary and Allen Ginsberg, but you were actually friends with Alexander Shulgin, which I find really interesting, and I was fascinated by that. That you knew people in the psychedelic field like that. Was Shulgin, he was publishing on human interaction with psychedelics, taking them with a group of his friends and publishing that. At the time, that was probably illegal. So how was he publishing that stuff on human research?
So it wasn't really illegal. The compounds he was making were not controlled substances.
Hmm.
Some of them may have actually become controlled substances, but in the beginning, when he first makes them, they're not. And under the Controlled Substances Act, you have to specify specific chemicals that you're making illegal. So if you make something that's not specified, now that was before the analogs bill came out.
Hmm.
Analogs bill said, anything similar, yada yada yada. But so it wasn't illegal. It was somewhat unorthodox, and he was publishing a lot of his studies in the journal Medicinal Chemistry.
Hmm.
At a certain point, the editors came down on him and said, you can't publish clinical studies here if they're not being done according to a standard protocol. And in the last couple of papers he published that had human data, he said, we had it approved by the IRB, and it was done this way and that way. But he really did not meet the criteria for clinical studies, and he basically had to stop publishing human data near the end of his career because the journals wouldn't take it, because they said, this is too iffy. You don't have a proper regulatory approval. You don't have it registered with clinicaltrials.gov, et cetera, et cetera, et cetera. And there's a misunderstanding. A lot of people think he had a license to make these compounds, and the DEA took his license away after they raided his labs years ago. He never had a researcher's license. He had an analytical laboratory license, because early on, the DEA would make a seizure someplace, and they would give him something to analyze and say, what is this they're making? So an analytical laboratory license works like that. You don't have specific substances listed that you handle, because you don't know what the agent's going to pick up in a confiscation, and they bring it to you. So it could be methamphetamine, could be cocaine, could be heroin. You don't even know. So you can't have registration for each one of those. It's just a broad category. And the way that works is when somebody gives you something to analyze, you have to log it in, say where you got it, how much it was, physical properties. Then when you finish analyzing it, you have to have it destroyed with someone witnessing it, or return it to where you came from. So there's a whole chain of custody that occurs. So when they raided his laboratory, they found things, and they would hold up a vial and say, what's this? And he'd say, well, I don't know. Where'd you get it? I don't know. And then they pick up another one. What's this? I don't know. Where'd you get it? I don't know. Of course, he knew where some of it came from, and he knew where some, but he was just saying, no, I don't know, I don't know, I don't know. So that's really what they fined him for not proper record keeping. And then they took his license away. So he never was authorized just to make new psychedelics. He had an analytical laboratory license. I had a researcher's license, which allowed me to make new things, but also I had scheduled substances on my license. So it's a little bit of misunderstanding in terms of what kind of license he had and what he was able to do, but it was an analytical laboratory license. And when he came in, he just didn't have the record keeping expected of someone, what it was, where it came from, and kept it controlled, and and didn't have people witness when he destroyed it. And also it was really a lapse in record keeping. Fortunately, there was a big campaign, and everybody raised a bunch of money and paid his fines. I think they fined him $25,000. So all of his friends sent some money in and covered the fines. So he didn't suffer financially, but he couldn't work with those compounds anymore.
What I think is also super interesting about the sort of psychedelic community and people involved is people like yourself, maybe you have an interest in it because you're just, oh, this drug has this function, whereas other people might have an experience, they use a psychedelic and they go kind of the psychonaut route. And then people like Shulgin are kind of in the middle. They're like, trying to do the science, but also sort of involved in that community.
Yeah, Sasha was a unique individual. I'm not aware of anybody else that's really doing that.
Yeah.
Um, I think the people that talk about doing research by taking psychedelics, it's their personal research, but it really, if you can't publish it and it's not done according to certain standards, I'm not sure it doesn't fit the definition of modern research.
Yeah, I totally
So,
agree. Yeah.
yeah, and I don't know that there's anybody who, picked up the ball. After Sasha died, um, when Sasha was alive, he created the Alexander Shulgin Research Institute. And there's a guy out there, I think Paul Daly, who still does some work. He says the Alexander Shulgin Research Institute is carrying on the groundbreaking work of Sasha Shulgin, which is kind of ridiculous because there's no one that can carry on the groundbreaking work of Sasha Shulgin. If you make compounds, it's not the same thing. It's not really the same. So I don't know that there's anybody that I would point to in the United States, at least, that's able to do that. You can't buy things like that. When I was in the 9th or 10th grade, I could buy chemicals at the drugstore. I could order chemicals. I could order glassware. I actually had a home lab. I
Wow.
wasn't making drugs, but I was making, explosives and, other kinds of weird things. But, and you could go down to the drugstore. If I wanted to make gunpowder, I could go down to the Rexall drugstore down in Covington, Kentucky, and buy saltpeter, powdered sulfur, and powdered charcoal. And you'd take it up to the counter and buy it, and the pharmacist would just wink at you because he knew you were making gunpowder. You can't do that anymore.
No. What
So
was what was so unique about I mean, you knew Shogun as a person. Like, what was so unique about his personality? Was he very like analytical? Was he a social person? Was he kind of
yeah,
internal?
he was a very outgoing person. Um, yeah, outgoing, very bright guy. Kind of a Renaissance man. He played a viola, uh, and he read poetry and really kind of just a really interesting guy and knew a lot of stuff. He liked to tell puns. If you could tell a pun, you could never keep up with him. He was probably the world's best punster. I went to visit him once when Rubik's Cube had come out, and we were sitting up late at night, and he liked to drink red wine at that time. I don't drink, and so he was feeding me glasses of red wine. And I was pretty blotto by about 2 a.m. or so. And he brought out this Rubik's Cube. It says, "Do you ever have one of these?" And I'd messed with one. He says, "Let me show you how to solve it." He went through and he started twisting, and like in just a few minutes, he had it solved. I
Wow.
said, "Well, how'd you do that?" So then he wrote out all the steps. He had a
Oh my
specific
God.
thing. You do this, you do that, you do this, and like 10 different steps. If you did it, you'd get it done. And so he was I guess you could say, a puzzle solver. Um, really very congenial, well liked by everybody who knew him. A really outgoing, generous guy. So um, unique individual.
Mm. Yeah, I think I told you I was so bummed I never talked to him before he passed away. That was definitely one of the. I wish I were involved in that, sort of stuff a little bit younger. But it's also interesting because people like Timothy Leary. I don't want to like rip on Timothy Leary, but I think he unfortunately did a disservice to the psychedelic community. He did bring it out and sort of get it to the mainstream community, which I don't think was a good thing. Um, and it seems like his fascination with it came from. I think he's a Harvard psychologist at the time, and he went down to maybe Mexico to take mushrooms, and that sort of changed his view on psychology. But to sort of take it from the academic community to the mainstream, I feel like was not the best route of doing things.
Yeah, it kind of pushed him over the edge. Um, he was apparently a brilliant psychologist who did a lot of work on personality development and personality assessment. And of course, had read the Life magazine article in 1957
Hmm.
about the mushrooms from Mexico. Went down, took the mushrooms, and sort of started his career by bringing mushrooms back. And then Sandoz made psilocybin, and he got that and was giving it to graduate students and so forth. And I think LSD came out and worked the same way and lasted longer and was more powerful.
Right.
I only met him actually once at a
Oh
meeting,
wow.
and we were sitting at a panel after the meeting was over, And it got to me, and all the people at the meeting were kind of psychonauts maybe.
Mm.
And so I started off, I said, I'm just a reductionist scientist. And Tim leaned out and looked over at me. He said, but David, you're not a reductionist scientist all the time. And I looked at Tim. I said, well, Tim, nobody's supposed to know that. That's my one exchange with Tim.
That's funny. That's great. I was one of the things I was watching the other day was a podcast with Joe Rogan and Dennis McKenna, and Joe Rogan actually mentioned, he's like, I want to have David on my podcast. I don't know if you ever thought about reaching out to him. You'd probably have to go to California at some point. I think that would be like just wonderful. I think people would love that.
Yeah. I've done some of these. I've done a lot of interviews, but I'm not as attractive as people who are more controversial, like Dennis McKenna. He's a good friend of mine. I like Dennis a lot. But he carries the McKenna name, and he's started the McKenna School of Natural Philosophy or something. And he spouts kind of the stoned ape theory and all.
Yeah.
He's got the whole dog and pony show, and I'm not as popular because I don't have the dog and pony show.
You're
mainstream reductionist scientist.
You're pretty popular in the world of psychedelics, I think. I think you have a lot of interviews and your name's definitely out there for sure.
Well, I started in the field in 1969.
Yeah.
Longer than about anybody's been in the field. Stan Groff, of course, been in longer, but in a different capacity. But from a science perspective, 1969 till now, how many years is that? 50 some years.
Yeah. And that's interesting because you hopped into the field during like the sort of psychedelic revolution in the 1970s, Hayden Ashbury, right, and all those sorts of things.
Yeah, well, there was none of that where I was, and of course Purdue was a Midwest Bible Belt, so I always had to look like I was a fairly normal straight person to survive at Purdue University in the pharmacy school. Can you imagine if I'd been in the pharmacy school and I had worn sandals and had a long pigtail in the back and tie-dyed shirt, like people would have been watching me real close.
Yeah, and you're traveling around with the Further bus and going to Grateful Dead shows. Sort of off the record, are you into any of that music? Are you into like Grateful Dead or Pink Floyd or anything of that nature?
I appreciate Pink Floyd probably more than I appreciate Grateful Dead. My son's a big Grateful Dead fan. He's got collections of their tapes. And Jimi Hendrix, I used to love Jimi Hendrix. I still have a bunch of his vinyl. And some of the 60s music I really appreciated. And now, I don't listen to music much. If I listen to Middle Eastern, nonverbal Middle Eastern stuff like that, international music, I'll listen to some, but I rarely play music around the house.
And you also play the fiddle, don't you?
No, I play a Native American flute.
Oh, you do? Okay.
And a blues harmonica.
Blues harmonica, that was it. I've heard that somewhere. Okay. Well, David.
There's that picture, that film, Dirty Pictures. Did you ever see it?
Yes, about Shulgin. Yeah.
Yeah, so I have appearance in there, and I play the flute and also the harmonica. If you hear the flute music in there, I think there's a scene where a train's going to hear this flute playing, and Etienne Sarre is the guy who made that documentary. I said, who's playing the flute? He said, that's you. I said, no way. No, that's you playing the flute. So if you go back and listen, if you hear flute music anywhere, and he asked me to play harmonica, actually Vice did a special on me, which hasn't been broadcast yet.
Oh.
But they wanted me to play flute and harmonica in their broadcast too. So come out with me also attempting to play music.
Mm. Somebody also interesting in the field that I've never talked to, but seems to be in sort of a middle ground. Like Shulgin is who's the vice? Hamilton Morris.
Oh yeah,
Hamilton Morris.
He's an interesting guy.
Have you met him? Have you talked to him ever?
Yeah.
Interesting. What's his whole spiel in terms of being involved at the interface between research and sort of taking a lot of the compounds himself?
I think he said he was going to go back to school, but I think his shtick is really like an educational one. He really wanted to experience these and talk to the people in the field and find out their background and what their goals were. just a kind of interesting guy, and managed to get Vice to pay for his trip. So
Wow. Yeah,
yeah,
he's an interesting character for sure. For sure. Well, David, thanks for talking to me. This was great, and it was super cool to actually have to have met you in North Carolina. I'm probably going to go back to the Reggio group. I want to do more computational work with them because that's been fascinating. That's been just like the coolest thing ever.
yeah, good,
So I'll probably reach out to you when I come back to North Carolina, and hopefully
sure,
all this pandemic in the world will be over by then.
hopefully.
Yeah.
Okay,
All right. Thank you so much, David.
nice talking to you. Have a
Yep.
good day.
Bye.
Stay safe.
Will do.